Time is a river flowing at different speeds across the cosmos. This is the startling reality of Einstein's theory of relativity, a concept we are now testing in the most extreme environments imaginable. By the end of this, you will understand how these deep space experiments are reshaping our most fundamental concepts of reality. We will investigate how a clock ticks slower near a black hole and why the signal from a distant pulsar holds a cosmic secret. What does it mean for our future if time itself is so fluid and malleable? Einstein's genius was to see the universe not as empty space with objects in it, but as a dynamic, flexible fabric. This fabric, which we call spacetime, is woven together from the three dimensions of space and the one dimension of time. Think of it as a vast, cosmic trampoline sheet. When you place a heavy bowling ball in the center of a trampoline, the fabric stretches and forms a deep curve. That is exactly what a massive object like our Sun does to the spacetime around it. The planets orbiting the Sun are not being pulled by some mysterious, invisible force. They are simply following the natural curves and dips that the Sun's mass creates in this cosmic fabric. This is gravity, not as a force but as geometry. The very shape of reality is molded by the matter and energy within it. This radical idea leads to an even more profound consequence for time itself. If spacetime is a single, interwoven entity, then warping space must also affect time. Where the fabric is stretched most deeply, like near a black hole or even just a dense star, time itself begins to slow down. A clock placed in such a strong gravitational field would tick more slowly compared to a clock in the weak gravity of empty space. This is not a mechanical error. It is a fundamental property of the universe, a direct prediction of Einstein's vision. This single, startling insight is the key that unlocks the deepest mysteries of cosmic time. This means that time itself has weight. It flows at a different speed depending on where you are standing in the universe, a direct result of gravity's pull on the very fabric of reality. We call this gravitational time dilation. Imagine time not as a constant, universal river, but as a thick, slow-moving syrup. Near a massive object, the syrup of time becomes denser, its flow dragging as if caught in an invisible current. The deeper the gravitational well you find yourself in, the thicker this syrup becomes, and the slower your clock will tick compared to someone in a shallower well. This is not a theory about clocks breaking. It is a statement about the nature of time itself. The interval between two events, the very definition of a second, is physically stretched or compressed by the presence of gravity. The mathematics behind this are elegant, revealing that a clock experiencing stronger gravity, like one at sea level, will lose a tiny fraction of a second compared to an identical clock on a mountaintop, where Earth's pull is marginally weaker. On our planet, this difference is almost imperceptible, a matter of nanoseconds over a lifetime. But venture out into the cosmos, where gravitational forces are unimaginably stronger, and this subtle effect is magnified into a dominant force. It is in these extreme environments, near neutron stars and black holes, that we can truly put Einstein's bold prediction to the ultimate test. So in 1976, we took Einstein's idea and launched it into the sky. NASA Gravity Probe was not a grand observatory but a single, exquisitely precise instrument, a hydrogen maser clock strapped to a rocket. Its mission was deceptively simple: to fly straight up to an altitude of 10,000 kilometers and then fall back to Earth. During that brief journey, it performed a silent, profound experiment, comparing its own steady ticking against the rhythm of an identical clock safely on the ground. The result was a whisper from the fabric of spacetime itself. Just as the theory demanded, the clock in space, feeling the slightly weaker tug of Earth's gravity, began to run faster. It gained time, accumulating an extra second for every 73 years compared to its terrestrial twin. Think about that for a moment. We built a machine so sensitive it could measure the universe stretching time itself. This was not a minor adjustment in a laboratory notebook. It was a direct and stunning confirmation that Einstein's geometric vision of gravity was real. The cosmic trampoline was not just a metaphor, it was a physical reality that changed how clocks tick. Gravity probe transformed a beautiful piece of mathematics into an observable fact, proving that time truly is a fluid that flows at different rates throughout the cosmos. This successful test gave us the confidence to look even deeper into the void, toward the most violent and massive objects in existence, where the slowing of time becomes not a subtle effect, but the dominant rule of reality. Yet our planet is a placid backwater in the cosmic ocean of gravity. To witness time warp on a truly dramatic scale, we must journey to the most extreme environments the universe can conjure. These are the ultimate natural laboratories where the rules of physics are written in extremes. Consider the edge of a supermassive black hole, a place where gravity's grip is so absolute that not even light can escape. Here, the slowing of time is not a tiny, meticulous measurement. It is a profound and overwhelming reality. A single hour for an intrepid astronaut orbiting just outside the point of no return could equate to years or even decades passing for those watching from a safe distance. The universe itself stretches the very seconds into lifetimes, but we do not need to venture into such terrifying voids to find these conditions. The universe provides other, slightly more accessible crucibles. Neutron stars are the collapsed cores of once mighty suns, cramming more mass than our own star into a sphere no wider than a city. The gravity on their surfaces is billions of times stronger than the gravity we feel on Earth. This creates a spacetime curvature so severe that it bends the paths of light and warps the flow of time in ways we can actually observe from across the galaxy. By watching how matter behaves as it spirals into these incredible objects, we are running a continuous experiment on a scale no human laboratory could ever achieve. We are asking the universe itself to show us, in the most violent conditions it can offer, whether Einstein's beautiful theory truly holds. Scattered across the dark ocean of our galaxy are cosmic lighthouses known as pulsars. These are not ordinary stars, but the rapidly spinning, incredibly dense cores left behind after a massive star explodes. As they rotate, they emit powerful beams of radiation from their magnetic poles. If that beam sweeps across our line of sight here on Earth, we observe a flash of light, a pulse, with a regularity that rivals the most precise atomic clocks ever built. This metronomic ticking makes them perfect natural instruments for probing the fabric of spacetime. The real test begins when a pulsar is not alone, but locked in a gravitational dance with another dense companion, like a white dwarf or even another neutron star. In this binary system, the pulsar is constantly moving, swinging closer to and then farther from its massive partner. This orbital waltz through a dramatically warped spacetime creates a perfect natural laboratory. As the pulsar moves through its orbit, two powerful relativistic effects come into play. First, its immense orbital speed, a significant fraction of the speed of light, causes its own clock to slow down due to special relativity, the same effect that would slow time for a super-fast spaceship. Second, and even more profoundly, as it swings closer to its companion, it plunges into a deeper gravitational well, and its ticks are slowed even further by the intense gravity, as predicted by general relativity. The result is a complex, rhythmic distortion in the timing of the pulses we receive. Astronomers have spent decades, sometimes even years, meticulously collecting these pulses, listening for the tiniest deviations in their expected arrival times. A pulse might arrive a fraction of a millisecond early or late, a seemingly insignificant hiccup, but these minuscule shifts are a direct message from the universe, a coded signal describing how spacetime is being stretched and squeezed by gravity. By decoding this signal, we are not just confirming a theory in a textbook, we are watching relativity in action, played out on a cosmic stage over thousands of light years. Years before a clock ever soared into space on a rocket, relativity was already being tested in our own planet's atmosphere. The year was 1971, and two physicists, Hafele and Keating, performed an experiment of stunning elegance and profound implication. They did not need a billion-dollar spacecraft, only 4 of the world's most accurate atomic clocks, and a handful of tickets on regular commercial airliners. They placed these clocks aboard planes that flew eastward and westward around the globe. Their mission was to measure the combined whisper of 2 relativistic effects on time itself. The first was from special relativity, the idea that time slows down for anything moving at high speed. As the planes hurtled through the sky, the clocks on board were moving faster relative to the clocks that remained securely on the ground. The second effect was from general relativity, the very phenomenon the space probe would later confirm, that time speeds up where gravity is weaker. At cruising altitude, tens of thousands of feet above the Earth, the gravitational pull is infinitesimally weaker than it is at the surface. Hafele and Keating were testing a delicate and counterintuitive balance, a cosmic tug-of-war on the flow of time. After the journeys were complete, the scientists gathered their precious cargo and compared the traveling clocks to their stationary counterparts. The results were undeniable. The clocks that had flown had disagreed with the clocks that had stayed behind, and the differences were exactly what Einstein's equations had foretold. The clocks that flew eastward, moving with the Earth's rotation and thus at a higher net speed, had experienced a stronger special relativity effect and lost time. The clocks that flew westward, moving against the rotation, experienced a different balance of effects and gained time. The discrepancies were tiny, measured in billionths of a second, but they were real. This was not a thought experiment anymore. It was a direct physical measurement proving that the passage of time for a clock in a commercial jetliner is fundamentally different from that of a clock in a laboratory. The Hafele-Keating experiment did something remarkable. It brought the vast cosmic scale of relativity down to the human scale of global travel. It proved that these are not abstract forces governing only black holes and pulsars. They are woven into the fabric of our everyday reality, ticking away silently on every flight you take, a hidden layer of physics operating just beneath the surface of our normal perception. But the universe had one more subtle trick hidden within Einstein's equations, a phenomenon even more elusive than the slowing of time. This is frame dragging, the idea that a massive rotating body does not just curve the spacetime around it, but actively twists the fabric, pulling it along for the ride. Think of our planet not as a static bowling ball resting on the trampoline, but as a sphere spinning in a vat of thick honey. As it turns, it would drag the surrounding honey with it, creating a slow, swirling current. According to relativity, Earth does the same thing to spacetime itself. This subtle twisting, known as the lens-thirring effect, drags the very local frames of reference, the foundational grid against which we measure motion. Proving this existed required an experiment of almost impossible precision, the central goal of NASA's gravity probe mission. The spacecraft was essentially a flying telescope containing the most perfect spherical gyroscopes ever created. each one polished to near atomic smoothness. These gyroscopes were set spinning and then left completely isolated, their spin axes pointed at a distant guide star. If spacetime was perfectly static, as in Newton's universe, those axes would have remained locked in place forever. But if Einstein was right, and Earth was indeed dragging the fabric of spacetime around with its rotation, the gyroscope's axes would be ever so slowly pulled out of alignment. For over a year, the satellite monitored this delicate cosmic ballet. The effect it was looking for was tiny, equivalent to measuring the thickness of a sheet of paper from 100 miles away. Yet the data revealed a drift. The gyroscopes were processing, their axes shifting by the exact minuscule amount that general relativity predicted. This confirmation of frame dragging was a monumental achievement. It showed us that relativity is not just about how mass warps space, but also about how motion stirs it. This dynamic interplay is crucial for understanding the most violent whirlpools in the cosmos, the environments around rapidly spinning neutron stars and black holes, where the very fabric of reality is not merely curved, but whipped into a frenzied, swirling vortex. The ultimate test of gravity unfolds at the very edge of existence, where the fabric of spacetime is torn and rewoven. Black holes represent this final frontier, objects so dense that their gravity creates a one-way boundary, the event horizon from which nothing, not even light, can ever return. For decades, these cosmic beasts were understood only through their effects on nearby stars and gas. But in April 2019, a global collaboration of telescopes known as the Event Horizon Telescope gave us our first direct glimpse. The now iconic image of the supermassive black hole at the heart of galaxy M87 is not a photograph of the black hole itself, for that is impossible. Instead, it is a portrait of its shadow, a dark silhouette set against a brilliant, swirling ring of light. This luminous ring is not the event horizon. It is the final orbit, a place where gravity is so intense that light itself is forced to travel in circles around the abyss. We call this the photon sphere, a region where spacetime is curved into a perfect, inescapable trap for photons. If a particle of light enters this orbit, it can loop around the black hole countless times before either escaping to our telescopes or finally plunging inward. The dark shadow at the image center is larger than the true event horizon, a profound silhouette cast by this ultimate light trap. The precise size and shape of this shadow are not random. They are a direct prediction of Einstein's field equations. General relativity dictates exactly how a black hole of a given mass and spin should warp the light around it, painting this specific picture of darkness encircled by fire. When scientists compared the M87 image to the mountains of supercomputer simulations, the match was astounding. The shadow's dimensions aligned perfectly with what Einstein's theory had foretold a century earlier. This was more than just a spectacular image. It was a direct visual test of general relativity in the most extreme gravitational environment possible. We are now looking at the universe's most violent phenomena and asking it to verify our equations. Every new observation, every detailed study of that dark shadow scrutinizes the very foundations of physics, probing whether our understanding of reality holds firm even at the point of no return. The silent cosmos is not so silent after all. It rings with the echoes of colossal collisions, a symphony written in the fabric of spacetime itself. For a century, we knew these gravitational waves must exist, ripples propagating outward from accelerating masses just as Einstein predicted, yet they remained too faint for any instrument to hear. That all changed in September 2015, when the twin detectors of LIGO, the Laser Interferometer Gravitational Wave Observatory, caught a specific whisper from the void. The signal was not a flash of light or a burst of radiation, but a literal stretching and squeezing of space. Imagine the entire Earth, and indeed the solar system, being subtly deformed by a wave that compressed us in one direction while expanding us in another, all by a distance far smaller than the width of a single proton. This is what LIGO was built to detect. The signal that arrived told a story of ultimate violence, the final inspiral and merger of two black holes over 1 billion light-years away. The waveform itself was a message from the edge of reality. It began with a low chirp as the black holes circled each other ever faster, radiating energy in these gravitational ripples. The pitch and amplitude of this cosmic siren rose to a crescendo as the two objects spiraled inward at a significant fraction of light speed, culminating in a final, ringing splash as they became one. This was not a static test of gravity like measuring a clock's tick. This was observing the theory in motion during its most dynamic and violent stress test. The precise shape of that waveform, how its frequency changed over those final milliseconds, carried an exact imprint of Einstein's equations. When scientists compared the data to supercomputer simulations of merging black holes governed by general relativity, the match was perfect. The universe had performed the experiment, and the results confirmed our deepest understanding of gravity. We are no longer just looking at the cosmos. We are now listening to its most secret conversations, hearing the truth of relativity in the ripples from the dark. Even our nearest stellar neighbors whisper the secrets of warped spacetime. Just over 8 light-years away, the brilliant star Sirius dominates our winter sky, a beacon that has guided humanity for millennia. Yet its true nature is a binary system, a cosmic dance between the bright star we see and a faint, ghostly companion known as Sirius B. This companion is a white dwarf, the Earth-sized ember of a dead star, containing a sun's worth of mass crushed into a sphere no larger than our planet. Its density is so immense that a single teaspoon of its material would weigh many tons on Earth. This creates a powerful gravitational field, a significant dimple in the local fabric of spacetime, making the entire Sirius system a perfect nearby laboratory for testing relativity. The two stars are locked in a 50-year orbital embrace, and as they whirl around their common center of mass, they trace out a path that is not a simple, repeating ellipse. Instead, the entire orbit itself slowly rotates, like a spirograph drawing that gradually shifts its pattern. The point where the stars are closest, called the periastron, steadily moves forward with each pass. While some of this motion can be explained by classical Newtonian physics, a crucial portion of the shift is a direct result of general relativity. The intense gravity of the dense white dwarf warps the spacetime through which its companion moves, causing the orbit to precess in a way that Newton's laws alone cannot fully account for. For over a century, astronomers have patiently charted the precise positions of these two stars, mapping their slow celestial waltz across the blackness. The accumulated data reveals that subtle drift, a tiny but persistent advance in the orbit that matches Einstein's predictions with remarkable accuracy. This is not a phenomenon reserved for distant pulsars or invisible black holes. It is happening right here in one of the most familiar stars in our heavens. The Sirius system demonstrates that the rules of relativity are not just for the extremes of the cosmos. They are woven into the very fabric of every gravitational interaction, a universal law at work in our own celestial backyard. This elegant idea that gravity and acceleration are two sides of the same coin forms the very bedrock of Einstein's theory. The entire magnificent structure of general relativity rests upon the Equivalence Principle. Imagine yourself inside a sealed elevator car drifting in the void of deep space. If the car begins to accelerate upward, you would feel your feet pressed firmly against the floor. You could drop a pen and watch it fall to the ground. Every sensation and observation would be identical to the experience of simply standing in a stationary elevator here on Earth. There is no local experiment you could perform inside that box to tell the difference. This is the core of the principle, that the force you feel from gravity is fundamentally the same as the force you feel from being pushed. This insight was Einstein's happiest thought, the key that unlocked his new theory of gravity. But a principle this foundational must be tested to its absolute limits. Any tiny crack in this foundation, any minute deviation from perfect equivalence, would not mean the theory is slightly wrong. It would mean it is profoundly incomplete, pointing toward entirely new realms of physics we have yet to imagine. The question physicists have been asking for decades is a deceptively simple one. Does spacetime treat all things equally? If you take two objects made of different materials, perhaps a sphere of platinum and a sphere of titanium, and drop them in a perfect vacuum, do they fall at exactly the same rate? Galileo supposedly tested this from the Leaning Tower of Pisa, but our modern quest for precision requires us to leave the planet's vibrations and atmosphere far behind. This was the goal of missions like the French Space Agency's MICROSCOPE satellite. In orbit, in the pristine quiet of free fall, the satellite carried its precious cargo, cylinders of different compositions, and used ultra-sensitive electronics to monitor their positions. The experiment was to see if these different masses would drift relative to each other while in the gravitational embrace of Earth. If the equivalence principle holds, they should remain perfectly locked in place, falling together in unison. After years of collecting data, the results were announced. The microscope team found no violation, confirming the equivalence principle with a staggering new level of precision. They showed that any difference in the acceleration of different materials is less than 1 part in a million billion. The fabric of spacetime, it seems, truly is impartial. Yet the quest is far from over. New, even more sensitive experiments are being planned, probing for a violation so tiny it would reveal a deeper layer of reality, a whisper from the quantum realm where gravity and the other forces might finally unite. So this cosmic stretching does far more than just shift the color of ancient starlight. It fundamentally alters the very rhythm of time across the universe. When we observe a galaxy billions of light years away, its light is not only reddened, but its clock appears to tick more slowly from our vantage point. Imagine the light from a distant supernova, a stellar explosion that should flash and fade over a specific, predictable timeline. When we witness such an event in an extremely remote galaxy, the entire sequence unfolds in slow motion. The explosion takes longer to reach its peak brightness, and its decline is stretched out, as if viewed through a cosmic lens that dilates time itself. This is not because the supernova is moving away from us through static space, like a siren dropping in pitch as the ambulance speeds off. That would be the simpler Doppler effect. What we are seeing is far more profound. The very fabric of space between that galaxy and us has expanded since the light began its journey. The wavelengths of light are stretched, turning blue light to red, but so too are the intervals between the arrival of each photon, the ticks of that distant cosmic clock. We are not just looking back in time, we are watching time itself unfold at a measurably slower rate. This observed time dilation in faraway supernova is one of the most direct and haunting confirmations that the expansion of the universe is an expansion of spacetime itself, a geometric reality that governs not only the vast distances between galaxies but the very flow of time across the cosmos. Yet for all its power, general relativity contains a deep and fundamental crack. It paints a breathtaking picture of the cosmos on a grand scale. but it is utterly silent on the strange, probabilistic rules that govern the subatomic world, the realm of quantum mechanics. These two pillars of modern physics are both spectacularly successful in their own domains, but they speak entirely different languages and obey contradictory laws. This schism is not just a philosophical problem, it becomes a catastrophic failure in the most extreme environments the universe can produce. At the very center of a black hole, where general relativity predicts matter is crushed into an infinitely dense and small point called a singularity, the laws of physics as we know them simply break down. Similarly, if we rewind the cosmos to its very first moment, the Big Bang, we again encounter this same point of infinite density. In these realms, the smooth, geometric fabric of spacetime described by Einstein becomes a chaotic, frothing sea where quantum effects must dominate, but our current equations offer no guide. This is the greatest unsolved problem in theoretical physics. To resolve it, we need a theory of quantum gravity, a single framework that can describe both the force that holds atoms together and the force that binds galaxies. Ambitious candidates like string theory propose that the fundamental building blocks of the universe are not points, but unimaginably tiny, vibrating strings. Their different harmonies could give rise to every particle and force, including gravity, weaving them into a single cosmic symphony. Another approach, loop quantum gravity, suggests that spacetime itself is not a smooth continuum, but is woven from a fabric of discrete, finite loops, like a tapestry of incredibly fine threads. This would prevent the infinities of a singularity, replacing the Big Bang with a big bounce from a previous universe. These ideas are mathematically beautiful, but they have remained largely untested, existing in the realm of profound speculation. This is precisely why our deep space experiments are so vital. Every time we point a telescope at a pulsar, analyze the ring of a black hole, or listen for gravitational waves, we are not just confirming Einstein was right. We are searching for the places where he might be ever so slightly wrong. We are hunting for any tiny, anomalous deviation in the data, a subtle wobble in a pulsar's timing, a faint echo in a gravitational wave, or a slight asymmetry in a black hole's shadow that does not quite match the predictions of pure general relativity. Such a minute discrepancy would not be a failure of the theory, but a triumph. It would be the first whisper from a deeper layer of reality, the long-sought clue that guides us from our current, fractured understanding toward a truly unified theory of everything. These mysteries of cosmic time and gravity are woven into an even grander tapestry, one that includes components we cannot see directly. The very structure and fate of the universe depend on two profound enigmas, dark matter and dark energy. Our most successful cosmological models, all built upon the foundation of general relativity, demand their existence to make sense of what we observe. Take a single spiral galaxy, for instance. According to the visible stars and gas alone, the outer regions should orbit the center much more slowly, just as Pluto moves more sluggishly around the Sun than Mercury does. Yet when we measure their speeds, we find stars on the galactic outskirts whipping around just as fast as those near the core. It is as if the entire galaxy is embedded within a massive, invisible sphere of something that provides extra gravity, a gravitational glue holding everything together. We call this unseen anchor dark matter. Its presence is also felt through gravitational lensing, where the light from a distant galaxy is bent and distorted as it passes through the invisible mass of a foreground galaxy cluster, acting like a cosmic magnifying glass. Then there is dark energy, an even more perplexing concept. We know the universe is expanding, but the shocking discovery at the turn of the millennium was that this expansion is not slowing down, it is accelerating. Something is actively pushing the cosmos apart, a repulsive force woven into the vacuum of space itself. This is where our deep space tests of relativity become a high-stakes game. The entire framework of modern cosmology rests on a three-legged stool: general relativity, dark matter, and dark energy. If Einstein's theory of gravity is perfectly correct on the largest scales, then dark matter and dark energy must be real, physical entities that we have yet to fully identify. Our search for them drives missions like the Euclid Space Telescope and the James Webb Space Telescope, which are meticulously mapping the cosmic web and the history of expansion. But there is another, equally thrilling possibility. What if future observations, perhaps of a distant pulsar timing array or a subtle anomaly in gravitational lensing, reveal a tiny crack in general relativity itself? Such a discovery would mean that we may not need invisible components to explain the cosmos. Instead, our theory of gravity, as beautiful and powerful as it is, might require modification when applied to the vast emptiness between galaxy clusters. Every experiment we conduct in the depths of space is not just a test of a century-old theory. It is a vote on the fundamental composition of reality itself. Our ability to measure time's elasticity leads to a far deeper wonder. Why does the universe possess such perfect conditions for this discovery to even be possible? This question lies at the heart of the Anthropic Principle, a philosophical lens on our cosmic luck. The fundamental constants of nature, the very numbers that dictate the strength of gravity and the other forces, appear to be fine-tuned with incredible precision. Consider gravity's pull. If it were just a tiny bit stronger, the universe would have collapsed back on itself in a fiery crunch moments after the Big Bang. No stars, no planets, no long-lived cosmos in which time could stretch and slow. If gravity were slightly weaker, matter would have flown apart too quickly to ever coalesce into the galaxies and solar systems that are our home. The existence of a stable universe, one that can brew complex atoms and foster life capable of sending clocks into space, hinges on a breathtakingly narrow range of possibilities. We are not merely passive observers of these laws. Our very presence as conscious beings who can formulate relativity, build gravity probes, and decode pulsar signals is a product of this specific cosmic recipe. The fact that we live in a universe where time dilation is not just a theoretical concept, but a measurable reality we can test in the depths of space, is itself a profound piece of evidence. This shifts our inquiry from a simple how to a staggering why. Why does reality have the particular set of rules that allow for such intricate physics and for minds to unravel them? It suggests that our investigation into the slowing of time is more than a scientific endeavor. It is a remarkable feature of a universe that seems curiously fit for inquiry itself. The next generation of cosmic listeners is already taking shape, poised to catch the faintest whispers of warped spacetime. The Laser Interferometer Space Antenna, or LISA, represents a quantum leap in our quest. Imagine 3 identical spacecraft flying in a perfect triangular formation with each side spanning 2.5 million kilometers. That is a distance larger than the gap between the Earth and the Moon. These 3 craft will be connected not by wires, but by laser beams, forming the most sensitive measuring device ever constructed. While ground-based observatories like LIGO have opened our ears to the high-frequency chirps of stellar mass black holes, their vision is clouded by the constant rumble of our planet. LISA will operate in the pristine quiet of space, far from seismic noise and Earth's gravity, allowing it to tune into the universe's low-frequency gravitational hum. This is the realm of the cosmic titans, the mergers of supermassive black holes that lurk at the centers of galaxies. These colossal events generate waves that oscillate over hours or even years, frequencies that simply pass through Earth-bound detectors unnoticed. By capturing these deep, rumbling signals, LISA will give us a front-row seat to the dynamics of spacetime in the strongest possible gravitational fields. We will not just confirm that gravity works as Einstein said. We will scrutinize its every detail around these monstrous objects, testing the theory with a precision 100 times greater than anything we have now. Any tiny deviation in the waveform, any subtle hitch in the ringing of the final black hole, could be the first clue to physics beyond Einstein, a crack in the cosmic code pointing toward the ultimate theory of quantum gravity. The quiet hum of an optical lattice clock is about to become the newest sound in the cosmos. This is not your grandfather's atomic clock. While the cesium clocks that guide our GPS satellites are marvels of engineering, the next generation uses a different kind of magic. They trap thousands of atoms of elements like strontium or ytterbium in a grid of laser light, an optical lattice, and use the vibration of light itself to mark the passage of time. Their stability is almost beyond comprehension, so precise that they would not gain or lose a single second over the entire age of the universe. This phenomenal accuracy is the key that unlocks a new era of deep space experimentation. By placing one of these clocks on the lunar surface or in a stable orbit around the Sun, we create the ultimate cosmic timepiece. Its steady ticking, measured against an identical clock on Earth, would reveal the subtlest stretching of time due to the Sun's gravity, the Moon's pull, and the overall curvature of the solar system's spacetime. We are no longer just testing if Einstein was right. We are probing for deviations in his equations at a level of precision that was once pure science fiction. But the implications ripple far beyond pure physics. Imagine a future where spacecraft navigate the void between planets not with sporadic radio signals from Earth, but by using the constant, reliable tick of these deep space clocks as a celestial GPS. This autonomous navigation would be faster, more accurate, and free from the delays of communicating across millions of miles. This precise timing could also form the backbone of a solar system internet, synchronizing data between outposts on Mars, mining stations in the asteroid belt, and Earth with perfect coordination. We are on the verge of weaving a web of time throughout our celestial neighborhood, a network built on the profound realization that time itself is the most reliable guide we have. Every time you open a map on your phone, you are harnessing a force that warps the very fabric of time. The global positioning system is a triumph of engineering built upon the counterintuitive rules of relativity. Each satellite in that constellation high above Earth is a moving clock in a weaker gravitational field, creating a perfect storm of relativistic effects. Without correction, the combined influence of their high speed and reduced gravity would cause their internal clocks to drift. The timing signals they beam down to your device would slowly desynchronize from the clocks on the ground, introducing errors that compound at a staggering rate. The entire system would become useless within a single day, its calculated positions drifting by several kilometers. The solution is as elegant as the problem is profound. Engineers preemptively adjust the frequency of the atomic clocks onboard these satellites before they are ever launched. They are intentionally designed to tick at a slightly slower rate than their identical counterparts on Earth, a deliberate calibration that perfectly counteracts the time dilation they will experience in orbit. When the satellite reaches its station, speeding through a weaker gravity, its pre-adjusted clock ticks in harmony with the terrestrial time standard. This is not a minor software patch, it is a fundamental hardware fix for a fundamental property of the universe. Every turn-by-turn direction, every located restaurant, every precisely timed financial transaction is a silent, continuous validation of Einstein's theories. The most abstract cosmic principle has become the invisible foundation of our daily navigation, a constant reminder that the flow of time itself is now a tool in your pocket. That same cosmic fabric that warps time also bends the very path of light. A massive object like our Sun acts as a lens, subtly deflecting the starlight that passes near it. During the total solar eclipse of 1919, astronomers confirmed this stunning prediction by measuring the shifted positions of stars near the Sun's blacked-out disk. The universe had revealed that gravity does not just pull on matter, it curves the trajectory of light itself. Today, we witness this phenomenon on a truly colossal scale, a powerful tool we call gravitational lensing. Enormous clusters of galaxies containing trillions of stars and vast seas of dark matter create such profound dimples in spacetime that they become cosmic telescopes. The light from galaxies far behind these clusters is bent and distorted as it travels through this warped space, often stretched into long, luminous arcs or multiple mirrored images of the same distant object. This is not just a cosmic illusion, it is a direct and measurable consequence of mass curving the geometry of the universe. By carefully analyzing these distorted images, astronomers can perform a kind of cosmic cartography. The specific pattern of the lensed light acts as a map, revealing the total distribution of mass within the foreground cluster. This includes not just the glowing stars and gas we can see, but the invisible scaffolding of dark matter whose gravity dominates the cluster's pull. Every arc and every duplicate image is a data point in a grand experiment, testing the precise relationship between mass, spacetime curvature, and the path of light. So far, on these immense scales, the universe continues to affirm Einstein's vision with breathtaking accuracy. The cosmos uses its own most massive structures to magnify its most distant corners, allowing us to peer deeper into space and further back in time than we ever could on our own. The late 1990s delivered a cosmological shock that still reverberates through physics. Astronomers were observing distant supernovae, expecting to measure how quickly the universe's expansion was slowing down under gravity's relentless pull. Instead, they found the opposite. The most remote stellar explosions were fainter than their calculations predicted, a sign they were farther away than they should have been. The inescapable conclusion was that the expansion of the cosmos is not decelerating at all. It is speeding up. Some mysterious, repulsive force is actively pushing galaxies apart, overwhelming the collective gravity of all the matter in the universe. This discovery of an accelerating cosmos was so monumental it earned the Nobel Prize, and the enigmatic force driving it was named dark energy. To fit this into Einstein's equations, physicists revived his cosmological constant, a term he had once inserted and later called his greatest blunder. This constant represents a fixed energy density inherent to the vacuum of space itself, a kind of anti-gravity woven into the fabric of nothingness. Yet the true nature of dark energy remains one of the deepest mysteries in science. Is it truly constant, as the cosmological constant suggests, or is it a dynamic field that changes over time, perhaps growing stronger or weaker as the universe ages? The answer will dictate the ultimate fate of everything. Will the acceleration continue steadily, leading to a cold, lonely dispersal of all galaxies, or could it intensify, eventually tearing apart the very fabric of spacetime in a theoretical big rip? To find out, a new generation of deep space observatories is being built. Missions like the Nancy Grace Roman Space Telescope and the Euclid spacecraft are designed to map the history of the universe's expansion with unprecedented precision. They will measure the positions and distances of billions of galaxies, tracing the subtle imprint of dark energy across cosmic time. This is not just a search for an invisible component. it is a direct stress test for general relativity itself on the largest scales imaginable. Any deviation from Einstein's predictions in this vast arena could reveal that dark energy is not a constant, but something far stranger, forcing us to rewrite our fundamental understanding of the cosmos and its final destiny. Even the most elegant theories can be momentarily fooled by a hot cup of tea. As the Pioneer 10 and 11 spacecraft sailed beyond the orbit of Neptune, their trajectories told a strange story. They were slowing down ever so slightly, experiencing a tiny but persistent deceleration toward the Sun that no one could explain. This was the Pioneer Anomaly, a whisper of a mystery that drifted through the outer solar system for decades. The unexplained pull was minuscule, comparable to a 10/1000th of the gravity you feel at Earth's surface, yet it was undeniably there. For years, this anomaly fueled intense speculation. Had we finally found a crack in general relativity's armor? Was some new, unknown force acting over the vast distances of interstellar space? Perhaps dark matter was exerting a subtle drag, or our understanding of gravity itself needed a fundamental rewrite. The possibilities were as thrilling as they were profound. The solution, however, was not written in the stars but in the spacecraft's own engineering. These pioneers were powered by the steady decay of plutonium in their radioisotope thermoelectric generators. This process produced not just electricity, but also a constant, gentle heat. After years of painstaking digital archaeology, reconstructing the craft's complex design and thermal properties, a team of scientists found the culprit. Heat radiating from the spacecraft was not perfectly uniform. A tiny fraction more thermal photons were bouncing off the back of their large dish antennas than from the front. This imbalance created an infinitesimal thrust, a photon push, that was gently breaking the probes. The effect was so small it had been lost in the noise for years, a testament to the incredible precision required to navigate the void. The Pioneer Anomaly stands as a critical lesson in cosmic humility. It reminds us that before we can declare a revolution in physics, we must first be certain we have accounted for every last whisper of heat, every conceivable nudge from the known world. In the search for truth at the edge of the solar system, the most profound discovery is sometimes the one that confirms our current understanding by revealing a hidden variable we had simply overlooked. But the smooth cosmic fabric Einstein described may only be an illusion, a grand average of a far more chaotic and grainy reality. This is the realm of the Planck scale, where the universe operates by rules we can barely imagine. The Planck length is almost inconceivably small, a trillion times smaller than a single proton. At this fundamental scale, the very concepts of here and there, before and after, begin to lose their meaning. Spacetime itself is theorized to boil with a violent, seething energy, a turbulent foam where tiny wormholes may flicker in and out of existence and microscopic black holes pop into being only to evaporate an instant later. This quantum foam is the predicted texture of reality when gravity is forced to obey the same quantum rules as every other force in nature. We are forever barred from directly observing this frenzy, as any probe powerful enough to see it would instantly collapse into a black hole. Yet we are not completely blind. The vast emptiness of space itself becomes our laboratory. When a gamma-ray burst explodes billions of light-years away, it sends a torrent of photons racing across the cosmos on a journey that lasts eons. If spacetime is truly smooth, as Einstein believed, then all these photons, regardless of their energy, should travel at the exact same speed and arrive at our telescopes in perfect unison. But if the universe is built upon a foundation of quantum foam, then this frothy texture would affect their journey. A high-energy photon, with its smaller wavelength, would stumble over the fine-grained bumps of the foam more frequently than a low-energy photon with a longer wavelength. Over 1 billion light-years, this minute cumulative drag could cause a detectable delay, a tiny lag between the arrival of the most energetic photons and their less energetic siblings. Astronomers are now scouring the light from these colossal explosions, searching for exactly this kind of energy-dependent spread in arrival times. Each gamma-ray burst is a natural experiment, a cosmic stopwatch testing the fundamental smoothness of the void. So far, the results are ambiguous, a tantalizing maybe that keeps the door open. Finding a confirmed delay would be a monumental breakthrough, the first observational evidence that spacetime has a quantum structure, forcing us to redraw our most basic picture of reality itself. On August 17, 2017, the universe sent us a message written in gravity and light. For the first time, the LIGO and Virgo observatories detected the ripples of 2 neutron stars spiraling into a final, violent embrace. This event, known as GW170817, was not just another gravitational wave chirp. It was the starting pistol for a new era, multi-messenger astronomy. Within 2 seconds of the gravitational signal, orbiting telescopes caught a powerful flash of gamma rays from the same patch of sky. The cosmos was speaking to us in 2 different languages at once. For decades, we had been listening to the universe with one ear and watching it with one eye. This event connected the two. The gravitational wave signal itself was a direct test of general relativity in an incredibly strong field, revealing the precise dynamics of these ultra-dense objects as they circled each other hundreds of times per second before merging. But the real magic was in the combination of signals. The fact that the gamma rays arrived just moments after the gravitational waves, after traveling over 100 million light-years, was a test of stunning precision. It confirmed that gravitational waves do indeed travel at the speed of light to within 1 part in a trillion. Any deviation would have shattered our understanding of the cosmos. Then came the afterglow. Ground and space-based telescopes swiveled to observe the aftermath, witnessing a new kind of explosion, a kilonova. This was not the familiar light of a supernova. It was a unique, rapidly fading glow produced by the radioactive decay of material forged in the neutron-star collision. The spectral signature of this light revealed the cosmic alchemy at work. For the first time, we had direct evidence that the incredible pressures and densities in such a merger are the cosmic forges where the universe creates the heaviest elements. The gold in a wedding ring, the platinum in a catalytic converter, these are not made in the hearts of stars, but in the furious crucible of colliding neutron stars. This single event provided a cross-checked ledger of cosmic information. We tested gravity with the waves, confirmed the speed of those waves with the light, and then used that light to understand the origin of the very atoms that make up our world. It was a complete story told by multiple messengers, and it proved that the most extreme laboratories in the universe are also our most revealing. Yet this elegant solution to cosmic acceleration reveals a terrifying rift at the foundation of physics. The cosmological constant, as we observe it in the dark energy pushing galaxies apart, is incredibly small. But when we calculate the energy that should be bubbling up from the quantum vacuum, the empty space between particles, the numbers are catastrophically different. According to the well-tested rules of quantum mechanics, the vacuum of space should be a seething, energetic froth. Every cubic centimeter of nothingness should possess a staggering energy density, a power so immense it should have torn the universe apart in its first instant of existence. The discrepancy between this theoretical prediction and the gentle, observed push of dark energy is not a small rounding error. it is a factor of 1 followed by 120 zeros. This is the cosmological constant problem, the single largest mismatch between prediction and observation in the entire history of science. To grasp the sheer scale of this error, imagine predicting that a single breath of air would contain enough energy to power a city for a century, only to measure it and find it has less energy than a single photon of light. Our two most successful theories, quantum mechanics and general relativity, are giving us two utterly irreconcilable answers for the exact same question: what is the energy of empty space? This is not a minor puzzle, it is a screaming alarm that our understanding of reality is fundamentally incomplete. The vacuum is not empty, but its true nature remains a profound mystery. Any future deep space observatory that measures the subtle evolution of dark energy with greater precision is not just collecting data, it is hunting for the clue that will guide us toward a new theory of quantum gravity, one that can finally explain why the void is so strangely and perfectly quiet. This galactic clock is not a single instrument but a sprawling network. Pulsar timing arrays transform the entire Milky Way into an observatory for the lowest frequencies of gravity. The concept is as brilliant as it is ambitious. Scientists monitor dozens of the fastest spinning pulsars, those with rotations measured in milliseconds, scattered across different constellations. Each one acts as an independent, hyper-accurate metronome, its rhythmic pulses traveling to us for thousands of years across the void. The key is not to watch one clock, but to listen to the entire symphony at once. A passing gravitational wave, a ripple in spacetime from a distant cosmic collision, will leave a specific signature. It will minutely stretch the space between us and some pulsars, making their pulses arrive a fraction of a second late, while simultaneously compressing the space to others, causing their pulses to arrive a fraction early. The pattern of these tiny, correlated shifts across the entire array is what reveals the wave. It is like feeling a gentle swell pass under a vast fleet of ships, each one bobbing in a subtly different sequence. The primary quarry of these arrays is the gravitational wave background, a persistent hum believed to be generated by the combined chorus of millions of pairs of supermassive black holes orbiting each other in the hearts of distant galaxies. Detecting this hum would open a low-frequency window onto the universe, allowing us to hear the slow, stately dance of the cosmos's most massive objects. But the implications run even deeper. The precise way these waves distort the pulsar timings as they propagate through the curved spacetime of our galaxy provides a unique and stringent test of general relativity itself. Does the wave travel at the speed of light as predicted? Does its polarization, the way it stretches and squeezes space, match Einstein's equations? Any deviation from the expected signal would be a whisper of new physics, a hint that our understanding of gravity itself requires an update on the grandest of scales. A million tiny suns are waking up across the darkness of the early cosmos. The James Webb Space Telescope is our window into this dawn, its infrared eyes sensitive to the heat of the first stars and galaxies that ignited when the universe was a fraction of its current age. This is more than a voyage of discovery, it is a fundamental test of our cosmic rulebook. The standard model of cosmology, known as lambda CDM, is built entirely upon the framework of general relativity. It tells a specific story about how gravity, dark matter, and dark energy conspired to build the universe we see today. According to this story, the cosmos should have matured at a particular pace. Small, chaotic clumps of dark matter should have slowly gathered over eons, pulling in normal matter to form the first stars, which then gathered into the first small, misshapen galaxies. These proto-galaxies would then merge over billions of years to form the majestic spirals and ellipticals we see in our modern universe. The James Webb is now reading that story directly from the source, looking back to a time when the universe was only a few 100 million years old. And what it sees is both thrilling and deeply puzzling. The early universe is not a sparsely populated frontier with a few scattered, infant galaxies. It is teeming with massive, fully formed, and incredibly bright galactic systems far earlier than anyone predicted. These are not the faint, struggling sparks our models foretold. They are cosmic cities that appear to have been built in a geological instant. How could gravity have worked so fast? How did dark matter clump together with such efficiency to build these colossal structures in what seems like no time at all? The very existence of these ancient giants forces us to question the entire timeline. If our understanding of gravity on the largest scales is perfectly correct, then something else in our model must be wrong. Perhaps the nature of dark matter itself, or the behavior of dark energy in the ancient past. Or, in a far more radical possibility, the rules of gravity in the early, denser universe were subtly different from what Einstein described. Every distant, brilliant galaxy spotted by the James Webb is a data point in the grandest experiment of all, a direct challenge to our understanding of the force that shaped reality. The telescope is not just showing us where we came from, it is asking us to check the foundational equations that describe our entire cosmic home. The puzzles of dark matter and dark energy have forced physicists to consider a radical possibility. What if Einstein's theory of gravity, for all its beauty, is incomplete? This has led to the development of bold alternatives, theories that seek to rewrite the rules of gravity itself rather than invoking invisible components. The most prominent of these is known as modified Newtonian dynamics, or MUND. Its core idea is elegantly simple. It proposes that the laws of gravity change when the acceleration becomes incredibly small, like the faint tug felt by a star in the sparse outer reaches of a galaxy. In this regime, gravity would become slightly stronger than Newton or Einstein predicted. This extra gravitational kick could, in principle, explain why those outer stars whip around so quickly, all without needing any dark matter at all. For individual galaxies, MUND works surprisingly well, often matching the observed rotation curves with remarkable accuracy. It feels like a neat solution, a way to tidy up the cosmos without filling it with unseen matter. Yet the universe is rarely so simple. When we zoom out to the scale of immense galaxy clusters, MUND begins to falter. The sheer amount of gravitational pull needed to hold these colossal structures together is far greater than what MUND alone can provide. There is also the faint, ancient glow of the cosmic microwave background, the afterglow of the Big Bang. Its detailed pattern is a perfect fingerprint of a universe dominated by dark matter, a fingerprint that MUND struggles to replicate without adding some form of hidden mass back into the equation. So the great contest continues. On one side stands general relativity with its dark universe, and on the other stand its challengers, the modified gravity theories. The future of cosmology hinges on this competition. Every new deep space mission, every precise map of galactic motions, and every subtle feature in the gravitational wave background serves as a new battleground. These observations are not just collecting data, they are acting as a cosmic jury, weighing the evidence for and against our fundamental understanding of the force that binds the cosmos. The final verdict on how gravity truly works is still being written in the stars. A black hole's final whisper threatens to unravel physics itself. Stephen Hawking's brilliant calculation revealed that these cosmic vacuums are not entirely black. Due to strange quantum effects at the very edge of the event horizon, black holes can slowly leak radiation, losing mass over unimaginable eons until they potentially vanish entirely. This Hawking radiation was a triumph that merged quantum theory with gravity, but it came with a devastating cost: the information paradox. The fundamental rule of quantum mechanics is that information is never truly lost. If you burn a book, every scrap of ash and smoke still contains, in principle, the information needed to reconstruct its pages, but a black hole presents a terrifying exception. Imagine throwing that same book into a black hole. According to general relativity, the book is gone, its information sealed forever behind the event horizon. Then, as the black hole emits Hawking radiation and evaporates, all that remains is a faint, random, and thermal glow. This glow carries no details, no fingerprints, no memory of whether the black hole consumed a book, a star, or 1,000 elephants. The specific information about what fell in has been erased from the universe. This is the paradox, a direct conflict between the sacred rule of quantum mechanics and the grim prediction of general relativity. One of them must be wrong. Resolving this has become one of the most urgent quests in theoretical physics. One promising idea suggests that black holes are not the perfect prisons we thought. The concept of soft hair proposes that when an object falls in, it imprints incredibly subtle patterns on the event horizon itself, like ripples on the surface of a pond freezing in place. These faint imprints, this soft hair, could potentially store information about what entered. Another profound approach comes from the holographic principle, the mind-bending idea that all the information describing a three-dimensional volume of space might be encoded on its two-dimensional boundary, like a cosmic DVD. For a black hole, this means all the information about everything inside it could be painted on its event horizon. If this is true, then as the black hole evaporates, that information is not lost, but slowly and chaotically radiated back out, scrambled into the Hawking radiation in a code we cannot yet read. The fate of a single atom falling into a black hole is now a question that probes the deepest nature of reality, forcing us to choose between the permanence of information and the finality of the void. These subtle shifts in time will one day be calculated into the flight plans of human missions to Mars. An astronaut spending 3 years on a journey to the Red Planet and back will return to Earth having experienced a few extra milliseconds of life compared to everyone they left behind. The difference is born from their constant high speed in orbit and the slightly weaker gravity they experience during their voyage. A fraction of a second seems trivial, almost laughable in the context of a human life. Yet for the machines that guide them, that tiny discrepancy is critical. Our entire network of interplanetary communication and navigation relies on the flawless synchronization of clocks. A millisecond drift can translate into a navigation error of hundreds of kilometers in the void between planets. Future mission controllers will not just be plotting courses based on fuel and trajectory. They will be actively correcting for the warping of time itself, baking Einstein's equations directly into the autopilot. This is relativity transformed from a cosmic curiosity into a line item in an engineering manual. But this is only the beginning. The true implications unfold if we ever harness the power for near-light speed travel. A ship accelerating to 90% the speed of light would become a time machine for its crew. For every year they experienced on board, more than 2 years would pass for those on Earth. A journey to a star a dozen light-years away would feel like a decade for the travelers, but everyone they knew back home would have aged over 20 years. This is not science fiction fantasy. It is the inescapable consequence of the same physics we are confirming today by listening to pulsars and watching black holes collide. Our deep space experiments are not merely about understanding the universe. They are a crucial rehearsal for a distant future where humanity must finally learn to live by the flexible rules of cosmic time. Beyond the terrifying finality of a black hole's event horizon, the universe might hide even stranger possibilities. Theoretical physics dares to imagine objects that push the boundaries of the known, hypothetical entities with names that sound like science fiction. Boson stars, for instance, could be immense spheres not of atoms but of ultralight particles, held together by gravity in a delicate, ghostly balance. Gravastars propose an even wilder idea, a star with a core of exotic dark energy sealed inside a thin, super-dense crust defying total collapse. And then there are the legendary wormholes, tunnels through the folded fabric of spacetime that could, in theory, connect two distant points in the universe. What these exotic compact objects all share is a crucial difference from a black hole. They would lack a true one-way event horizon. There would be no point of no return, only a point of extreme gravity from which light might still, after a tremendous struggle, eventually escape. This subtle distinction is the key to finding them. When two black holes merge, the resulting gravitational wave signal is clean and definitive, a sharp chirp that rings down into silence as the new, larger black hole settles into its calm, featureless state. But if one of the objects was an exotic imposter, the signal would tell a different story. The collision might produce faint, telltale echoes in the gravitational waves, subtle ripples caused by energy and information scrambling to escape the object's surface rather than vanishing forever. It would be like hearing a single, clear bell chime in a pure black hole merger, but hearing a series of diminishing, reverberating chimes if an exotic object was involved. As our gravitational wave observatories like LIGO, Virgo, and the future LIS, a space antenna, grow ever more sensitive, they are not just listening for the crashes we expect, they are actively scouring the data for these tiny, anomalous whispers. They are hunting for the one signal that does not fit the pristine template of general relativity's black holes. Finding even a single, confirmed, exotic compact object would be a revolution in astrophysics. It would force us to tear out the chapter on stellar death and rewrite it entirely, proving that the cosmos holds endings for massive stars far more bizarre and wonderful than we ever dreamed. Our own daily experience tells us time is a river flowing the same for everyone, but relativity shatters that illusion, forcing a confrontation with reality itself. The famous twin paradox is not just a thought experiment anymore. With clocks on jets and rockets confirming its truth, it presents a genuine philosophical puzzle. If one twin travels to a nearby star at near light speed and returns, they will be measurably younger than the sibling who stayed on Earth. Both perspectives are equally valid within their own frames of reference. There is no single universal clock ticking for all of creation. This dismantles the classical idea of a single present moment, a universal now that everyone shares. What does it mean for our understanding of cause and effect if two observers cannot even agree on the order of events separated by vast distances? This is not a trivial detail. It strikes at the heart of causality, the bedrock principle that causes must precede their effects. Relativity carefully preserves this locally, but on a cosmic scale, the linear progression of time we take for granted becomes a fluid and personal experience. We are left to wonder if time is a fundamental building block of the universe or something that merely emerges from a more basic, perhaps quantum, structure. Each experiment that confirms time dilation does more than add data to a textbook. It refines our very conception of what is real, blurring the line between physical measurement and a profound inquiry into the nature of existence. Our journey through these cosmic tests reveals a universe far stranger and more wonderful than we ever dreamed. From the steady ticking of an atomic clock soaring high above the clouds to the faint, rippling echo of black holes crashing together in the void, every single experiment has cemented Einstein's theory of general relativity as a true masterpiece of human thought. It is a framework of breathtaking elegance that has passed every trial we have thrown at it, from the edge of our solar system to the brink of the abyss. Yet for all its power, the story is not over. The profound puzzles of dark energy, the desperate search for a theory of quantum gravity, and the tantalizing hunt for exotic objects all remind us that the final chapter of this cosmic saga remains unwritten. The universe is our ultimate laboratory, a place of endless challenge that dares us to look deeper, to think harder, and to never stop testing the very fabric of reality. So the next time you find yourself looking up at the night sky, remember you are not seeing a static picture. You are gazing into a dynamic, relativistic cosmos where time itself is a fluid river, and you are an invited explorer in this grand, ongoing